Greetings and welcome to All Things Physics, where we go to great lengths to uncover aspects of the physical world that are normally hidden from view. Today I'm going to discuss something truly remarkable, something I never would have thought possible. Check it out. What you're observing here is an acoustic standing wave visualized in real time using a stroboscopic Schlieren imaging system. In other words, this is what sound actually looks like. Isn't this crazy? I mean, who would have thought that sound could actually be seen? I have to admit that I was totally flabbergasted the first time I saw this experiment. But what exactly is going on here? In this video, I'll provide a detailed description of precisely what you're seeing and then demonstrate how this remarkable video was made. Our story begins by delving into the details of sound. Quite simply, sound is a physical disturbance that travels through air or some other material, similar to the way a physical disturbance travels through this spring. Are you ready?
Yeah. Oh my god.
Did you feel that?
Yeah. Oh my god.
But to truly appreciate how sound travels, we first need to understand air at the molecular level. To do so, let's contemplate the air in this room. Specifically, let's consider a cubic meter of air. Air is a gas composed mainly of nitrogen and oxygen molecules, but includes small amounts of other substances. For our purposes, we'll think of all of these particles as being identical and assume that air obeys the so-called ideal gas law, which describes how the various properties of the gas are related to each other. Using the ideal gas law, we can determine the number of particles in a cubic meter of air, assuming normal pressure and temperature. Although this calculation is relatively simple, it's really hard to appreciate just how large this number is. There are approximately 25 septillion gas particles in each cubic meter of air. That's 25 million particles. To try to give you a feel for how large this number is, let's switch gears for a moment and consider something completely unrelated. How many grains of sand are there in the Sahara Desert? This might seem like an impossible question to answer, and indeed, it is impossible to get an exact answer. However, it turns out to be relatively simple to estimate an answer. We need to know the area of the Sahara Desert, we need to know how much of that area is covered with sand, and we need to know the average depth of sand in the Sahara. I happen to have some sand right here, and we can just do a quick measurement to figure out how big a grain of sand is. We find that a grain of sand is approximately half a millimeter, so that's 8 times 10 to the 3 grains per cubic centimeter. When we multiply that out, we get 8 times a quarter, that's 8 over 4 is 2, 2 times 1.5 is 3, 3 times 9 is 27, and then a 10 to the 12 times 10 to the 2 is 10 to the 14, times 10 to the 9 is 10 to the 23, and this is 2.7 times 10 to the 24 grains of sand, or 2.7 septillion grains of sand in the Sahara Desert. Wow, that's a lot of sand. Although this is a very large number, remember that there are 25 septillion air particles in 1 cubic meter of air. Thus, there are approximately 10 times as many air particles in a cubic meter as there are grains of sand in the Sahara Desert. You might wonder how this is even possible, and the answer is because air particles are so incredibly tiny. Therefore, if we want to get an understanding of what air actually looks like, we're going to need to zoom in an awful lot. With this in mind, let's slice up our cubic meter into smaller pieces. If we make 10 slices along each axis of the cube, we end up with 1,000 smaller cubes. Unfortunately, we're going to need to zoom in much more than this, so instead, let's make 100 slices along each direction, leaving us with 1,000,000 smaller cubes. Let's take a moment to simply marvel at this dizzying array of 1,000,000 cubes. Looking directly toward one of the faces, there are 10,000 stacks, with each stack containing 100 cubes. Of course, we're ultimately going to need to zoom in much more than this, so let's focus our attention on just one of these cubes. This cube has an edge length of 1 centimeter, which is slightly smaller than the size of a standard board game die. Now we want to zoom in and repeat the process of slicing this cube into 1,000,000 smaller cubes. 1 trillion of these smaller cubes would fit into our original cubic meter. If we again focus on just one of these cubes, it will have an edge length of 1/10 of a millimeter. To provide a little perspective on this size, I donated some of my hair and we put it into an electron microscope to get a close-up view. As you can see, one strand of my hair has a width of almost exactly 1/10 of a millimeter, which means this cube has an edge length that's approximately the width of a human hair. We still need to go even smaller, so let's slice this cube into 1,000,000 smaller cubes. 1 quintillion of these cubes would now fit into our original cubic meter. Zooming in once again, we see that these cubes have an edge length of 1 micron, 1/1,000,000th of a meter. I had to scour the web to find something this small that might be familiar to people, and I came across this beautiful electron scanning micrograph of some red blood cells. Based on this image, we see that our cube is now smaller than the width of a red blood cell. Unfortunately, even at this tiny scale, air particles are still too small to see, so once again we need to slice up this cube into 1,000,000 smaller cubes. 1 septillion of these cubes would now fit into our original cubic meter, and we're finally at the stage where the air particles become visible. I hope you're impressed, because this is as close as you'll ever get to seeing air at the molecular level. This cube has an edge length of 10 nanometers, and on average it contains 25 air particles, with a diameter of less than half a nanometer. These particles travel at nearly 500 meters per second, much too fast to see, so in addition to zooming in, I've also slowed things down by a factor of 100 billion. Thus, each passing second corresponds to approximately 10 picoseconds of gas time. Interestingly, if you watch the blue particle, you'll see that there are surprisingly few collisions with other gas particles. This is because the particles only occupy a tiny fraction of the total volume, less than 1/100th of a percent. But remember, things have been slowed down a lot. On average, air particles travel approximately 70 nanometers between collisions, a distance we refer to as the mean free path, which means that in reality, each air particle undergoes approximately 7 billion collisions per second. It turns out that sound waves in air are a direct result of the collisions between particles. Unfortunately, the fact that we see so few collisions when air is drawn to scale makes it essentially impossible to simulate an actual sound wave at the molecular level. Thus, we will ultimately need to rely on a more qualitative picture to understand the behavior of sound waves in air. Before moving on, I thought it was worth showing a larger volume of air, so here's a cube with an edge length of 50 nanometers containing over 3,000 particles. To me, seeing a larger volume provides a better perspective for how air particles fill space. We can even zoom inside the box to get a sense of what it would feel like to be an air particle. I'll give you a few moments to enjoy the view, because it's unlikely you'll ever get this perspective again. Now that we have a reasonably accurate mental picture for what air looks like at the molecular level, it's time to investigate sound in a little more detail. Because sound is a wave phenomenon, I'd like to start by looking at waves on a spring. The simplest type of wave to understand is a transverse wave, which means the disturbance is transverse, or perpendicular, to the direction the wave travels. We saw an example of this type of wave earlier in the video.
Oh my god.
Here's a slow-motion view that demonstrates the coils in the spring move mainly up and down, whereas the wave itself moves from right to left. Of course, if you look carefully, you'll see that the coils also move a little bit to the left and right, a result of the spring being able to support compressional or longitudinal waves in addition to transverse waves. A compressional wave occurs when there's a change in the coil spacing, which causes a change in tension that's propagated along the spring. Notice that the coils now move in the same direction as the wave travels. Of course, the coils themselves return to nearly the same location once the wave has passed. One thing that makes compressional waves more challenging to understand is that the shape of the disturbance is harder to make out compared to a transverse wave. That's because the coil displacement in a transverse wave is perpendicular to the wave motion, so the spring takes on the exact shape of the wave. However, that's not the case for a compressional wave. One way to depict the shape of a compressional wave is by plotting the coil density. For such a plot, a high value represents coils that are close together, while a low value represents coils that are spread apart. As seen here, for compressional waves, it's almost always the case that a high-density pulse is immediately followed by a low-density pulse. And if a steady stream of such pulses are produced in rapid succession, then we get something that looks a bit like a traveling sine wave. In a gas, the particles can only push against each other, which means a gas can only support compressional waves. To view such a wave, we need to be able to discern small differences in the density of air particles. Unfortunately, as already mentioned, this is essentially impossible to simulate for air under normal conditions. Therefore, to make these density changes visible, I had to significantly increase the number of gas particles. Shown here are 3,000 particles released with random velocities, confined inside a two-dimensional rectangular box with a movable left wall. You can think of this as a cylinder with a movable piston. Once the particles are uniformly distributed, I'm going to push on the left wall to compress the gas. As you can see, when the gas is compressed, it leads to a large density wave which travels down the cylinder, reflects off the right wall, and then travels back to the left. Notice that the particles themselves only move a relatively small distance, as you can see by the blue tracer particles. It's the high-density pulse that travels down the cylinder. Because of the random motion of the particles, this density wave slowly disperses. But if you watch carefully, you can see that it undergoes multiple reflections. Now, an actual sound wave consists of a complicated combination of such pulses, but in the simplest case, we can repeat the pulses at a regular rate. Unfortunately, because of the reflections with the walls, we normally end up with many interfering wave pulses traveling back and forth in the cylinder, and this quickly leads to a complicated mess that's very difficult to understand. However, if the frequency of pulses is adjusted so that the reflected pulses match up perfectly with the incoming pulses, we end up with a simple repeating wave pattern. In the specific example shown here, we see that the gas oscillates between two specific states, one having a high density on the left and a low density on the right, and the other having a low density on the left and a high density on the right. This behavior is a resonance phenomenon we refer to as a standing wave. Generally speaking, standing waves arise due to interference between left and right moving waves. These traveling waves combine to create a stationary oscillation, hence the term standing wave, shown here in yellow. The defining feature of a standing wave is that there are locations where the wave never changes, called nodes, and locations where the wave undergoes maximal changes, called antinodes. But even though a standing wave doesn't move left or right, it continually oscillates between high and low values. And in the case of a sound wave, these oscillations can occur thousands of times per second. Standing waves usually occur because of reflections at some sort of boundary, which means they only arise when some geometric constraint is satisfied. One way to demonstrate this is to excite transverse waves on a spring with fixed ends. In this case, we find that standing waves form only for frequencies that lead to an integer number of half wavelengths along the length of the spring. In a moment, we'll see that standing sound waves have the same behavior when reflected from a hard surface. I realize this introduction has been a bit lengthy, but because we're about to see what a sound wave looks like, I thought it was important to give you the nitty-gritty details of what constitutes a sound wave. But we're almost there. The final piece of the puzzle is to experimentally visualize these minuscule density changes in the air. Well, if you watched my earlier video on Schlieren imaging, then you already know that a Schlieren system is what's called for here. But in order to visualize a complete sound wave, we need to make some modifications. In a previous video, I discussed the subtle physics underlying a Schlieren imaging system and how such a system can be used to see things that are normally invisible. The basic idea is to use a spherical mirror to focus a light source onto a wire light block that sits in front of a camera. Normally, none of the light from the source makes it into the camera, so the camera just sees whatever's in front of the mirror. However, small changes in the air's density, such as those caused by changes in temperature, will cause the light to bend slightly so that it bypasses the light block and makes it into the camera. In this way, a Schlieren imaging system can be used to expose the airflow around a candle flame or the behavior of cold air around an ice pack as it falls toward the ground. To fully understand the subtle details on how Schlieren imaging works, I recommend you watch my previous video. But hopefully this brief description provides enough information so you at least have some sense of what you're seeing. But the question remains, can a Schlieren system be used to see a sound wave? Unfortunately, try as we might, our initial attempts all ended in failure. So we packed up our mirror and took a road trip to Harvard University to meet up with Wolfgang Ruckner, an expert on this topic. In fact, it was an article written by Wolfgang that originally got me interested in constructing a Schlieren imaging system, so I was really looking forward to meeting him in person. Of course, it was also fun just to visit Harvard. So we're here at Harvard University in the physics department, and I'm here with Wolfgang Ruckner, who has worked here for a long time.
I've worked here for 39 years and have been retired for 7 years.
Okay, great. So you are an expert at all things physics.
I would not call it an expert, but I know my way around.
Okay, good. Because we need your help.
Okay.
I hear that you're going to help us see something truly fantastic today.
Yeah, we are going to try to actually see sound waves going through the air. Actually see them.
Actual sound waves.
Yes, actual sound waves.
And we're going to be able to visualize them.
That is the plan.
Okay. Well, this sounds absolutely fantastic.
Good.
And I know there's quite a bit of setup.
Yes, it's not a trivial thing to do.
Okay, so let's get to it and see what we find.
Okay.
In order to see a sound wave, we first need to set up a basic Schlieren system, and it needs to be finely tuned to maximize sensitivity. An important aspect of the experiment I hadn't fully appreciated until this visit. In addition to the Schlieren system, we need to generate an appropriate acoustic wave and set up the timing circuit so that we can strobe the light source on and off at the frequency of the sound wave. By introducing a delay between the sound wave and the strobe light, we should then be able to view the sound wave at any point in its phase. Moreover, making use of the stroboscopic effect should allow us to view the sound wave moving in slow motion. So here's the part of the Schlieren system, and I know from my own experimenting with these that they're very subtle. Can you talk a little bit about just what distances we're talking about here?
Well, the amount of refraction up or down because of changes in the pressure is of the order of only 1 or 2 thousandths of an inch. So the challenge is, let's make the image of the slit on the wire just the right size so that if the image moves up 1 or 2 thousandths of an inch, that light gets in.
So you really just want it just a little bit bigger than the wire.
Yes,
Yeah.
just a little bit. Or exactly the
Or
size.
exactly, which is tough.
Yes.
So we think we're sort of set up here with the basic Schlieren setup, and we're just going to do a quick test. What you're looking at right now is the mirror, and I'm just going to put my hand in front of the mirror, and oh my goodness, look at that. That is spectacular. With the Schlieren system working, we place an ultrasonic transducer in front of the mirror, which is essentially a speaker that produces a sound wave beyond the range of human hearing. In our case, at a frequency of approximately 30 kilohertz. Above the transducer, we mount a glass plate to act as a reflector, which can be adjusted vertically to search for standing waves. Unfortunately, there was some construction going on in the building on the day we filmed this scene, and because the experiment is so sensitive, the vibrations caused some significant flickering in our Schlieren images. Nevertheless, a series of bright and dark fringes is clearly visible as the glass plate is lowered. Is this a sound wave? Although it's tempting to think the bright and dark fringes correspond to high and low densities, the situation is more subtle. To understand what we're seeing, we need to remember that bright areas in a Schlieren image indicate regions where the density is changing. We refer to these density changes as gradients, and with the current setup, both positive and negative density gradients look the same. To help clarify what's going on, here's an animation of what's happening in slow motion. Recall that the yellow curve here represents the density or pressure of the air, as demonstrated earlier for a simulated standing wave. Notice that the bright fringes appear where there's a density gradient, between the regions of high and low density. Moreover, because the standing wave is continually flip-flopping, the fringes actually disappear twice per cycle. Of course, this blinking occurs 60,000 times per second, so we don't notice it. Thus, what we're actually seeing here is a time average of the absolute value of the gradient of the standing wave. Now, as impressive as this experiment is, and it is pretty impressive, to me, it doesn't quite feel like we're seeing a sound wave. The problem is that what we've done here so far only works for a standing wave. So if we remove the glass plate, then we don't see anything. Why? Because now we're dealing with a traveling wave, so the locations of the fringes move through space. The result is that the fringes get smeared out in space, so everything looks exactly the same.
To actually see a traveling wave, we need to strobe the light source at the same frequency as the sound so that we always see the sound wave at the same point in its cycle. The result, shown here, is that the sound wave is always in the same position whenever the light is on, which makes it look frozen in space. To demonstrate that what we're seeing is in real time, we can bring in a plexiglass plate and watch the sound waves reflect off the plexiglass. And if you look carefully, you can even see the waves diffract around the edge of the plate. Making use of the stroboscopic effect, we can unfreeze the traveling waves by strobing at a slightly smaller frequency than the sound wave. In this way, we can reproduce a slow-motion evolution of the sound wave, and by changing the strobe frequency, we can change its apparent speed. Again, it's worth emphasizing that this is a real-time display of an actual sound wave being viewed using a strobed Schlieren imaging system. It turns out that we can even take things one step further. Recall that our Schlieren system is capable of distinguishing between positive and negative density gradients. The details are discussed in my earlier video, but the important point is that positive and negative density gradients are deflected to opposite sides of the wire light block. Therefore, placing colored filters on the sides of the wire leads to different colors for positive and negative gradients. Here's an example showing a candle flame, where the red indicates a decreasing density as you move to the right, and the green indicates an increasing density. With this in mind, I'd like you to predict what a sound wave will look like after adding colored filters to our Schlieren system. Here's an animation of the standing wave by itself. When we incorporate the filters, we can see how the positive and negative density gradients result in different colors. But notice that the colors flip-flop back and forth, and for our system, this happens around 60,000 times per second. Thus, if the light remains on continuously, we should see bright fringes that are a combination of red and green light. And if you've ever studied color addition, then you know that red and green light make yellow. And this is exactly what we see experimentally. But if we strobe the light source at the exact frequency of the sound wave, then we freeze the standing wave in place, allowing us to clearly see the entire waveform in all its glory. Let's just pause for a moment to appreciate the wonder and beauty of what we're looking at here. I never would have thought that it's possible to actually see sound. Of course, it wasn't easy.
Well, now that I've seen how this whole thing gets set up, I'm pretty impressed. It's trickier than it looks.
Absolutely.
What are some of the issues you have to think about when you're setting this up?
So the first trick is to strobe the light not only at the frequency with which these waves are being produced, but vary the phase to find out where the maximum pressure change is happening.
I see.
And that's where we see it the best, and that's when we want to have the light, strobe light on.
I see. So that you match the light being on to the gradient.
Exactly.
I see.
Yes,
Okay.
that's the right word.
And that's not easy.
No, it's not easy. It takes some experimentation to find out where that is.
The last thing I want to show you is what happens when we strobe the light with a slightly smaller frequency from the sound. The result is a slow-motion view of the standing wave as it oscillates through its cycle. Notice how the colors flip-flop back and forth, demonstrating clearly how a sound wave is nothing more than an oscillating pressure wave in the air. I have to admit that this is one of the most incredible things I've ever seen. And if I've done my job right, then I'm hoping you agree. Wow! Can you believe what we just witnessed? Actual sound waves made visible using a stroboscopic Schlieren imaging system. Absolutely amazing. If you want to see more content like this, then I hope you'll subscribe and share the video with others who might appreciate it. And if you're truly inspired, you might also consider supporting this channel through Patreon. Your support helps keep this channel sponsor-free. I owe a huge shout out to Wolfgang Ruckner for teaching me so much about Schlieren imaging and for helping out with the experiments. This video could not have been made without him. And finally, before signing off, I want to leave you with a bit of a puzzle. If you look carefully at the standing waves in this video, you'll notice that the pattern of colors tells us there's a pressure antinode at both the top and bottom. At the top, the sound wave reflects from a hard surface, so a pressure antinode is expected. However, the bottom surface is the ultrasonic transducer, which oscillates at 30 kilohertz. So it seems like this boundary should give rise to a displacement antinode, which is a pressure node. So the question is, why does the transducer give rise to a particle node instead of a particle antinode? I have a guess as to what's going on here, but I'm not very confident. So if there are any acoustics experts out there who know what's going on, I'd appreciate it if you'd leave a comment below. And with that, I'll bring this video to a close. I'm David Jackson, and this is All Things Physics. Okay, you got them going the wrong way. You want to get it going away. There. Oh, that was it.
Oh, you don't want to
There you go. Okay. Take two. I like that one. Okay. Cut. I like that one a lot. Oh my God, it's looking great in here.
Maybe this is moving.
Unbelievable.